Okay, so let's actually go over what the application is. All right, so I mean, we just solved the differential equation kind of in a vacuum. We understand it. Let's go over the application, where the application has to do with population growth. So far, we've looked at population growth that is not tempered by anything, okay? It's not tempered by resources. It's not tempered by the environment. It's not tempered by threat of extinction, like if the population, because remember we said if the initial population is not high enough, you might actually get into a scenario where you don't have enough people to reproduce. So it's not tempered by competing species competing for resources or predator species, right? So we just had basically like idyllic population growth in a vacuum with unlimited resources, more like a lab environment. Obviously, we're not going to look at all those conditions at the same time, because then you probably have a system of equations, okay? Especially if it's not one equation. But we are going to look at we're going to add one realistic condition. So various factors limit the rate growth of a population, including birth rate, death rate, food supply, predators, and so on. The growth rate constant R, we've looked at that before. That's the birth rate minus the death rate, okay? So that's just, if you were to leave the population alone with unlimited resources, what would the natural reproduction rate be? R differs from different species, all right? If you got a species that produces one offspring, like an elephant or something, as opposed to a species that produces like what, 1 million offspring in one. So yeah, R is going to differ. R is going to differ. And then at the very end, I just like a little biology term. If a species is R selection, I think it means that its R is very high. Okay, so R differs from species to species. Okay, and then biologists have found that in many biological systems, so not in a lab environment, but in actual real world, the population grows until a certain steady state population is reached, okay? That steady state population is called the carrying capacity. The carrying capacity in a given environment, right? So a carrying capacity is a function of the species, and it's also a function of the environment. A carrying capacity of an organism in a given environment is defined to be the maximum population of that organism that the environment can sustain indefinitely. Okay? So, K represents the carrying capacity for a particular organism in a given environment. So we'll look at the very end. If a species has a K selection, it means it relies on the carrying environment to sustain its life as opposed to on the reproduction rate, which means you are okay with just giving birth to one offspring because you are counting that the environment can sustain its life so that it gives an offspring, as opposed to R selection, where I think you're not counting on the environment. That's why I produce a lot of them. But anyway, so K, if you've seen those R and K terms before, it is the same as the biology terms. So K represents the carrying capacity. R is a real number that represents the growth rate. P of T represents the population of the organism as a function of time. P naught represents the initial population of the organism at time t equals 0. So this is our differential equation. dP, the change in P, the change in population, equals R times P times 1 minus P divided by K, and P of 0 is P sub naught. And this is called the logistic differential equation. All right, let's take a look at some of its properties. First of all, when is the change in population 0? When do we... It doesn't mean the population is 0, right? It doesn't mean the population has died out. It means just the birth rate and the death rate match, because there's no growth in either direction. So when is the change in population 0? Let's take a look at our differential equation. When is the right side equal to 0? When the right side is equal to 0 under two conditions. We're assuming R is never 0, right? We're assuming R is never. So when P of T equals to 0, the right side is equal to 0. P of T equals to 0 means you have reached extinction. Or when P of T is equal to K, look at that, because if P of T is equal to K, you have K divided by K, which is 1. 1 minus 1 is 0. So your two equilibrium solutions are extinction or when you have reached the carrying capacity. Because remember, the carrying capacity is the number of members of a species an environment can sustain indefinitely. So the solutions P of t equals 0 and P of t equals k are called equilibrium solutions. We're not going to look at the slope field just yet because we don't know what r and k are, but we will. But what we're going to look at is sometimes this is used to demonstrate how stable or unstable the solutions are. So P of t equals 0, we'll see by looking at an actual example, is an unstable equilibrium solution. And then P of t equals k is an asymptotically stable equilibrium solution. That means that, remember what a stable equilibrium solution means is if you have an initial condition in the neighborhood of k, then the population will approach k as time goes on. And then P of 0 is unstable. That it means if you have a population in the neighborhood of 0, the population will still try to approach k. Okay? That's what that means. You might be thinking something is missing. Something is missing. There's another equilibrium solution missing, and there is, and I'm going to have you look at that for your homework problem. But there's something called a threshold, which means you have another equilibrium solution, because if your species has too few members in it, it will start approaching 0. So there should be something in between, and then but for now we're assuming that even if you're slightly above 0, you're able to. There's no threshold solution. If you're slightly above 0, you're able to reproduce. Okay, so let's take a look at an application. This is what we just solved. We solved y for t. Let's take a look at an application.